So to summarize what we have learnt on single phase full wave rectifiers or 2-pulse diode rectifiers, we have looked at two circuits which can perform full wave rectification. That means utilize the positive half cycle of input voltage to produce a DC output voltage and also the negative half cycle of input voltage. And there are two circuits. In one circuit there are two diodes, but you need a center tapped transformer, and in the other circuit you would not need a transformer, but you need 4 diodes. The two circuits are shown here. In the center tap transformer rectifier, we have a primary winding with N1 turns, and we have a secondary winding which has a total of 2 N2 turns, and from the center tap the load is connected on the negative terminal and the positive terminal of the load is connected to this common cathode point. And in the case of bridge rectifier, 4 diode full wave rectifier, we have 2 diodes connected in common cathode connection and 2 diodes connected in common anode connection, and the source is connected between them, between these 2 points, the AC source. And where is the load connected? The load is connected across the common cathode point and also the common anode point. We have looked at the operation of these circuits under different load conditions, whether you have a resistive load or R load with L filter or R load with C filter. We have looked at all those cases. For N1 is equal to N2, when the number of turns of primary winding are equal to half of the number of turns of secondary winding, both the circuits, the first circuit and second circuit, will have the same current and voltage waveforms, like at the input IS and VO respectively. So IS and VO will be same in both the cases. Then how do the circuits differ? The circuits differ in terms of the repetitive maximum reverse voltage VRRM or peak inverse voltage PIV across each diode, the voltage that is appearing across each diode when it is off. So here if you see, this is written as VD1A and here it is indicated as VD1B. So VD1A is 2 times the input voltage. And how do we say that? When VD1 is off, when D1 is off, D2 is on. So the voltage across VD1 is simply sum of these two voltages or the complete secondary winding voltage, which will be twice the input voltage if N1 is equal to N2. But that is not the case for a bridge rectifier, because when D1 is off, D3 is on. So this point is same as this point. So VD1B will be equal to simply Vs. So the maximum voltage that appears across each diode in the case of a bridge rectifier is just Vm, while that in the case of a center tap transformer rectifier is 2Vm. Of course, when the turns ratio is unity. That is what we have to understand. That is the basic difference between these two. Otherwise, they behave the same way. There is another difference. In practical diodes, the voltage across a diode is not 0 when it is on. So if you look at the on state, in the case of first rectifier, current flows like this. And of course, a similar current flows on the primary side. So in the conduction path, and of course the second path is open. So this is open. It's not conducting. So current is circulating like this. So in the path of current flow, there is only one diode that is appearing. And in the negative half, again current flows like this, as we have already seen. So again there is only one diode appearing in the current path. So strictly speaking, if you want to consider the voltage drop across a diode also, you need to include one diode drop, or you need to subtract one diode drop from the secondary voltage to calculate the output voltage. Whereas in the other case, 4 diode or bridge case, current flows through one diode and it completes the circuit after flowing through the another diode. In the positive half cycle, it flows through D1, D2 as shown. In the negative half cycle, current starts flowing through D3, again it goes through the load, completes the circuit flowing through D4. So there are always two diodes in the path of current flow. So we need to subtract the drop across two diodes in the case of a bridge rectifier. This diode voltage drop is significant when you are dealing with low voltage circuits. That is why the center tapped rectifier is preferred for low voltage applications. If you want to step down the voltage, for example, you want to make a 5 volt power supply, the center tap transformer rectifier is a choice because you will be losing only 0.7 volts or so. Let us look at the input current waveforms for the three types of load that we discussed so far: R load and C filter with R load and L filter with R load for a full wave rectifier. When the load is just a resistor, we have a pure sinusoidal current drawn from AC source. But how does the voltage look like? The voltage is not a pure DC, it varies all the way from 0 to Vm. When we have a C filter with R load at the output, the current drawn from source is definitely an AC waveform, but it is not sinusoidal. The waveform has sharp peaks and the peak value IP increases with increase in the value of capacitance. However, you have a smoother and smoother DC voltage that appears at the output. If you have a large C, then your minimum value of the voltage will be lesser. And how about L filter with R load? When you have an L filter with R load, your waveform is again AC but non-sinusoidal, and the waveform looks like this in the case of an L filter with R load. And how does the output voltage look like? The output voltage is the voltage across the resistor, that is after inductor. So the output voltage looks like this. It is smooth, but its average value is 2 Vm by pi. Whereas with C filter, your average value is more than 2 Vm by pi. It has a chance to have more than 2 Vm by pi, and when you have a huge capacitance value, your average value can almost be approximated by the peak value. So you have the possibility of getting a voltage of 325 volts, which is the peak of the phase voltage, if you have a 230 volts RMS supply. Whereas if you have an L filter with R load at output, as you increase the value of L, the output current ripple will be decreasing. So the peak to peak ripple will be decreasing, but the average value does not change. The average value of output voltage does not change, and the average value of output current also does not change. And what is that average value? It is 2 Vm by pi. So for an L filter with R load, as you increase the value of L, we said that the ripple, this peak to peak ripple will be reducing. Same is the case in the negative half also. So for a very large value of L, this can be approximated by a square wave. And what is the value of the peak of the square wave? The maximum value of the square wave? It is 2 Vm by pi into R. Why? Because this is the average current flowing through the output, and the average current flowing through the output is the average voltage here divided by resistance. And the average voltage here, in the case of a full wave rectifier is the average of this completely rectified sinusoid, since the average voltage across inductor is 0. So the average voltage that appears across the resistor is 2 Vm by pi, and the average current flowing through the resistor would be 2 Vm by pi times R. So that is the constant value of this square wave that we are considering. It is an approximation of the current drawn by the full bridge rectifier when you have a large inductance at the output. And in the case of C filter with R load, this value of I peak can be calculated as a function of delta, as we have already discussed, and the expression is given here. Now if you take this square wave, we can analyze it using Fourier series to quantify what is the desirable component and what is the unwanted component. So the fundamental component of this square wave will look like this. It is in phase with the AC source voltage. That is an interesting point to note. So the displacement power factor is unity, because diodes D1 and D2 immediately start conducting here, and D3 and D4 again exactly start conducting at pi. So always the zero crossings happen at the zero crossings of voltage only. So the displacement power factor is unity, and the distortion factor of course is not unity. As the current is not sinusoidal, it is the value of the fundamental component of RMS divided by the total RMS. And what is the total RMS value of this waveform, square waveform? The total RMS value is simply IO, the maximum value, which is indicated here. And we can find the RMS value of fundamental component using Fourier series, and it will turn out to be 4 by pi times IO is the peak, and 1 by root 2 is the RMS value. And that this 4 by root 2 pi is almost 0.9. And then any nth harmonic RMS can be computed like this: IS1 RMS by n. That is a property of the square wave. Each harmonic magnitude is just 1 by nth of that of the fundamental. So the total power factor will turn out to be 0.9. And the total harmonic distortion again can be calculated based on the total RMS value and fundamental RMS value. You just need to calculate the RMS value of the ripple component or undesirable component and divide it by the fundamental component. So the unwanted component in this square green color waveform is almost 48.43% of the desirable component. So this is how we can compare the input current drawn from source for all these three types of loads. Then again, looking at the output voltage, the output voltage is varying all the way from 0 to Vm in the case of resistive load, if you just have a resistor at the output. But if you put an L filter, your voltage across resistor will be smoothened, but the average value of voltage will remain 2 Vm by pi. You cannot get anything more than that. If you want to get more output voltage, one needs to go for a C filter. So in the case of C filter, the average voltage is a function of delta and gamma as expressed here. And how are delta and gamma found? They are also expressed here. Tan gamma is 1 by omega RC, and delta is the instant at which diodes turn on in each half cycle. So that can be solved iteratively as explained earlier. And the average value of output voltage is a function of delta and gamma as expressed here. And when you increase the value of C, the peak to peak ripple reduces, and we can almost say that we are getting a Vm as our DC output voltage. However, you end up drawing sharp peaks of current on the input side, as we have explained, because the diode conduction time gets reduced. So the charge that is lost by the capacitor has to be replenished within a very short interval. So the rectifier ends up drawing huge peaks of current. So the diodes have to be rated for much larger current, peak current value than the value of Vm by R. Let us take a look at the case of RLE load. It's a special type of load, as we said earlier. It represents a DC motor, and as long as the current in inductor, this inductor L, is continuous, it doesn't make a difference for the source. So when the source is negative, D2 conducts, and when the source is positive, D1 conducts, because this current should always flow. Same is the case in the case of bridge also. When Vs is positive, D1 and D2 conduct, because this current has to flow. And when Vs is negative, D3 and D4 conduct, again to ensure the continuity of flow of current through the inductor. The difference in circuit operation is seen in discontinuous conduction mode. What do we mean by that? When this inductor current goes to 0 within one line cycle. So we have shown the case of discontinuous conduction for a half-wave rectifier also for easy comparison. What is the principal difference? The principal difference is that the voltage VO dash, if you look at VO dash, it never goes to 0. In the case of a bridge rectifier, it never goes to 0, whereas it was 0 for some time in the case of a half-wave rectifier. Why VO dash can be 0? Because D2 is directly connected across those two terminals, and when D2 is on, obviously VO dash is almost 0. Whereas in the case of a bridge rectifier, that state does not exist. Why? Because when Vs is negative here, the state of D2 being on existed. But what happens in the case of a full bridge rectifier when Vs is negative? D3 and D4 will conduct. So negative of the input voltage will appear across VO dash. So VO dash can never be 0 in a full bridge rectifier. And the average value of output voltage, VO average, which is same as VO dash average, is a function of Vm, delta and beta. We have given expressions for single phase half-wave rectifier earlier. Similar expressions can also be derived for the bridge rectifier. And what is delta? Delta is the angle at which any of the diodes can conduct. In fact, delta is the angle at which D1 can conduct in the positive half cycle in the case of half-wave rectifier. In the case of full-wave rectifier, delta is the angle at which any pair of diodes can conduct, because one pair of diodes can conduct in the positive half and the other pair can conduct in the negative half. And what is delta? Delta is simply sine inverse E by Vm, because conduction can happen only when this input voltage is greater than E. Now let us look at the angle beta. And what is beta? Beta in the case of half-wave rectifier is defined as the extra time that current flows in the negative half cycle. So the current goes to 0 at pi plus beta. And how can you get this value? We get the expression of current waveform and take its exponential fall, because the exponential fall interval exists only here, and equate it to 0 at an angle pi plus beta and solve it iteratively to get the value of beta. Whereas in the case of a bridge rectifier, exponential fall interval never exists. Why? Because this VO dash is always like this, is equal to the section of sine wave or equal to E. Beta depends on the instant at which current becomes 0, and that can happen even before pi in the case of a full bridge rectifier. So beta is this angle. Diode current starts flowing when input voltage is more than E, that is at this instant delta, and it follows a sinusoidal plus exponential, and it is becoming 0 even before pi, and the difference between pi and the instant at which it is turning off is defined as beta. The current stays 0 for some more time, and the other two pair of diodes D3, D4 will start conducting at pi plus delta, because at that time negative of input voltage becomes more than E, so they start conducting and the cycle goes on. So current being 0 can actually start in the positive half cycle itself, and that is what is referred to as discontinuous conduction in the case of a full bridge rectifier, as shown by this waveform. And what is the average current? The average current that is flowing at the output is VO average minus E by R, that is the average value of inductor current, and the source current has a waveform exactly same as that of the inductor current waveform in the positive half, and inverse of that in the negative half. So it's again an AC waveform which looks like this. Again, the waveforms can be analyzed for THD and distortion factor and so on.